In this video, we're going to take a look at commercial AM radio and then the Superheterodyne receiver, which is the type of receiver that you'll be implementing in this lab. So in commercial AM radio, or commercial broadcast AM, the U.S. Federal Communications Commission specifies that the carrier frequency of any station must be one of the following 117 values: 540 kilohertz, 550 kilohertz, by increments of 10 kilohertz all the way up to 1700 kilohertz. In the first station, x1 of t gets DC biased by a constant A, and then modulated by cosine of omega c1t, which then gets outputted by the transmitter. The second station, x2 of t, gets also DC biased by some constant A, and then modulated with cosine of omega c2 times t, which is what gets outputted by the transmitter, and so on. And at the receiving end, we have I of t equals the summation over I of y of t, goes through the receiver, and then gives at the output some xi of t, where this receiver has the capability of selecting different stations xi of t. Now, how can we build a receiver that can actually be tuned to select our desired station? One way of doing this is through what's known as the Superheterodyne receiver. The Superheterodyne receiver continues to be the most popular type of receiver used in analog radio communication systems. The basic block diagram of a Superheterodyne receiver is: here's the input I of t, which consists of a superposition of a bunch of amplitude modulated audio signals, gets picked up by the antenna, which first goes through an ILC front end, which is a bandpass filter, then has multiplication by the local oscillator, passes through an IF filter, which is a bandpass filter at IF frequencies, followed by an envelope detector, an audio amplifier, a DC blocking capacitor, and then our final output is the audio signal, which would get emitted by the speaker. Now, I'm going to talk about this ILC bandpass filter at the very end, since it's kind of hard to understand why this ILC bandpass filter is necessary until we know exactly how the local oscillator and IF filter work and then what effects that could cause. So let's take a look at the local oscillator. The local oscillator input is the sinusoid, whose frequency is varied to select the channel that one wants to listen to. In commercial AM radio, stations modulate and transmit audio signals with carrier frequencies in the radio frequency RF band, and so the job of the local oscillator is both to select the station that one wants to listen to, as well as convert the IF signal into an IF, or intermediate frequency signal, by mixing it with another locally generated sinusoid at frequency omega low. Let's look at a frequency domain representation of the operation of the modulator in the transmitter and then the local oscillator in the receiver. So here's the baseband signal spectrum of the original audio signal x of t. If I add a DC shift A and then modulate with a sinusoidal carrier at frequency omega c, we get our spectrum x of j omega shifted to frequencies omega c and minus omega c, as well as two impulses at omega c and minus omega c due to the DC constant A. So this is the signal spectrum at the transmitter after AM modulation. If we look at the signal spectrum at the output of the local oscillator, for the case where omega low is less than omega c, we see that the AM signal spectrum has been moved to frequencies omega c minus omega low and minus omega c plus omega low, as well as these two farther out frequencies here. The next step in the Superheterodyne receiver is to pass the output of the local oscillator through an IF filter, which is a bandpass filter that only passes frequencies near a certain IF frequency FIF. Now notice that by choosing a certain local oscillator frequency, we can use the local oscillator to shift the frequency of the modulated signal so that it passes through the IF filter undistorted. And assuming that the carrier frequency FC is greater than the center frequency of the IF filter FIF, the two possible choices of the local oscillator frequency would correspond to omega IF equals omega c minus omega low, which implies that the local oscillator frequency equals the carrier frequency minus the IF center frequency, or omega IF equals minus omega C plus omega low, which implies that the local oscillator frequency equals the center frequency plus the IF frequency. We can see this by looking at frequency domain plots of the actions of the local oscillator and the IF filter. Here's a plot showing how the local oscillator is used to mix into the IF band when F low is chosen to be the lower of the two possible frequencies, Fc minus FIF, and the second plot shows how the local oscillator is used to mix into the IF band when the local oscillator frequency is chosen as the higher of the two frequencies, Fc plus FIF. As you can see, after the IF filter, in both cases, all we're left with is the station that we selected being carried at carrier frequency FIF. Then we can put the output of the IF filter through an envelope detector, amplify it, block the DC component, and then play it to an audio speaker, which completes the superheterodyne receiver. Now, if we look at the second figure more closely, we see that when F low equals Fc plus FIF, not only does the signal centered at Fc get mixed into the IF band, but also any signal centered at F image equals FIF plus F low, which equals Fc plus 2 FIF, would also get mixed into the IF band. And this is because it would get shifted to the left by F local oscillator and then to the right by F low, which would interfere with the IF band. And the frequency band centered at F image is what's known as the image band. From this equation for F image, we see that the image frequency F image minus Fc equals 2 times FIF, which means that the separation between the carrier frequency of the desired station and the center frequency of the image band, which will also end up in the pass band of the IF filter after the local oscillator, equals twice the center frequency of the IF filter. And this corresponds to the case where the local oscillator frequency equals Fc plus FIF. And if you recall, both of these two plots corresponded to the case where Fc is greater than FIF. Also, if we look at the first figure, where F low is Fc minus FIF, we see that the image frequencies would be F image equals Fc minus 2 FIF if Fc is greater than 2 FIF, or F image equals 2 times FIF minus Fc if Fc is less than 2 times FIF, which means that the separation between the carrier frequency of the desired station and the center frequency of the image band equals Fc minus F image is 2 times FIF if Fc is greater than 2 times FIF, or 2 times Fc minus FIF if Fc is less than 2 times FIF. So from this, we conclude that when Fc is greater than FIF and the local oscillator frequency is Fc plus FIF, then the IF filter can't separate two AM stations whose carrier frequencies differ by 2 FIF. And when the local oscillator frequency is Fc minus FIF, then the separation between the desired and the image stations could either be 2 times FIF or even less, 2 times Fc minus FIF. And this is why we need the tunable RLC front-end filter in order to reject or attenuate the signals in the image band. And in physical AM radios, both the local oscillator frequency and the resonant frequency of the RLC bandpass filter are synchronized together when a station is selected. Now you might wonder, if we already need an RLC bandpass filter at the front of our superheterodyne receiver, why do we need to have a local oscillator to shift our AM signal to the IF frequency band and then have a fixed IF bandpass filter to select our station? Couldn't we just take the output of the RLC bandpass filter and then demodulate directly? And the reason is that it's very hard to build a tunable bandpass filter that also has high frequency selectivity, because in commercial AM radio, two stations are separated only by 10 kilohertz. So this bandpass filter has to be tunable in order to select different stations, but at the same time, it has to maintain a very narrow bandwidth regardless of its center frequency. And this is something that's very difficult to do in practice. With a superheterodyne receiver, we can build a single IF filter with a fixed center frequency and high frequency selectivity, and then use the local oscillator to shift between different stations. And it turns out that by having a single IF filter with high frequency selectivity, our front-end RLC circuit doesn't even need to have too much frequency selectivity in order to reject the image frequency. The standard IF filter in commercial AM radios has a center frequency FIF equals 455 kilohertz, which means that assuming we choose the local oscillator frequency as F-low equals FC plus FIF, then the difference between the image frequency and the center frequency equals 2 times FIF, which equals 910 kilohertz. So the desired station and the image frequency are separated by 910 kilohertz. This means that we don't even have to have a good RLC bandpass filter. All we need is a tunable bandpass filter that can be tuned to have different center frequencies. But even a low bandwidth around the center frequency of the RLC filter would still be enough to attenuate the image frequency 910 kilohertz from our center frequency. So this concludes our discussion of the superheterodyne receiver, and in the next video I'm going to move to the in-lab portion, and we'll start by building the IF filter in section 4.1 of your lab handout.